So in this video we're going to focus on solving logarithmic equations. So we're going to start with a very simple logarithmic equation. I'm going to go ahead and rewrite the equation. So we have log base 10 of x equals 1.6. And what we want to again remember is that log base b of x and exponential or exponentiation base b to the x are inverse functions. So if I take and put the logarithm into the exponent position on the exponential function, doing b to the log base b of x, the exponentiation base b is going to cancel the logarithm base b, and the x will come out as the result. So in this case, what I want to do is identify the base. The base is 10, so I want to exponentiate base 10 on both sides of the equation. And 10 to the log 10, the base 10 exponentiation will cancel the base 10 logarithm, leaving me with an x. And I'll have x equals 10 to the 1.6, which is the exact answer. And if I want to approximate it, I'm going to go into my calculator. And we're going to grab here the log key. In blue right above it, there is a 10 to the x button, so I'm going to go second log to get 10 to the whatever I need, 10 to the 1.6 in this case, and then I'll hit enter and I get 39.8ish. So I'll bring the PowerPoint back up. 39.8ish, and we get about 39.8. So there's a simple one. So again, we'll complicate things a little bit. So the idea is here, we want to use this, these are base 10 logarithms that we're looking at. So we know we want to use the inverse function 10 to the x to cancel those logarithms. But before I can do that, I need to have the logarithms isolated. Right now I do not have a single logarithm. I have multiple logarithms. They're not isolated. So I'm going to manipulate using algebra to get all of the logs on one side because they have the same base, and everything that doesn't have a log base 10 on the other. So I'm going to go ahead and rewrite the equation. So log base 10 of x minus 1 equals the opposite of log base 10 of x minus 9. I'm going to go ahead and add 1 to both sides, which is going to give me a 1 on the right hand side. I'm going to add, because I have a negative log x minus 9, I'm going to add log x minus 9 to both sides, which is going to give me log x plus log x minus 9. And now I can use log properties. Here I have the sum of two logs with the same base. And in video 1, we established a property that said if we have the sum of two logarithms with the same base, that those can be compacted into a single logarithm that will be the log of the product of the inputs into the logarithms. So it'll be x times x minus 9. And now I have isolated the log base 10. I have a single log base 10 all by itself. Now I can exponentiate base 10. So I'm going to make the right hand side an exponent base 10, and I'm going to make the left side an exponent base 10. Remember, a logarithm is an exponent, so that it makes sense that we would be putting it into an exponent position. And exponentiation base 10 will cancel log base 10, so the stuff inside the log function will fall out for us. And we get 10 to the first is 10. And then now, when I look at this now, I should recognize that I have a quadratic equation in a single variable. I have an x squared minus 9x equals 10. And now I'm going to be able to use factoring and using the zero product property. I can use the quadratic equation. I can use completing the square. I can use all of those tools that we learned earlier in the term regarding how to solve quadratic equations in a single variable. And this one, I'm going to go ahead and try factoring. So I'm also going to subtract this 10 from both sides to get things equal to 0. And I know factoring is going to work because I worked it out ahead of time. So I have a leading coefficient of 1, so guessing is efficient. And I have a minus 10. I need a product that makes minus 10 that will add, for which the factors will add up to minus 9. So I think minus 10 and plus 1 are going to work. And we need to be careful with logarithms because we can generate extraneous solutions, and we'll discuss that here in just a second. So I'm going to generate my two solutions from this. I factored it, and I'm going to use the zero product property to say one of the two products must be equal to 0. And I get x equals 10 or x equals negative 1. Here I want to stop for a minute. So some of the work that we've been doing has been finding the domain of log functions, and what we need to remember is that when you're inputting something into a log function, you're inputting the result of applying an exponential equation, and exponential equations generate non-negative numbers. They can't generate negative numbers. 3 to the x can't generate negative outputs. It can't generate 0 even. So the inputs to a log function, remember the domain of a log function is the inputs have to be greater than 0. So I can look at this and I can identify two things that must be true. Either x has to be right here, x has to be greater than 0, or x minus 9 also has to be greater than 0. We have to input non-negative numbers into our logarithms. It's the only type of input they're willing to accept. So if I solve this, I see that x must be a number bigger than 9. And you look at these two, one of them's more restrictive. This says x has to be bigger than 0. This says x also has to be bigger than 9. So we're going to put the more stringent restriction on things, and we're going to say, hey, the only numbers that will work are x's that are bigger than 9. 10 is bigger than 9. That works. X equal to negative 1. That's a number that is not bigger than 9. That is going to be an extraneous solution. It came out of the solution process because we generated a quadratic, but it turns out he's not actually a solution. X equal to 10 is our only solution. We could also get at this if we were uncomfortable with trying to identify domain. We could just plug things in and see if they work. So you get the log of, and I said 10 is a solution, so I should be able to plug 10 in there. Minus a 1 equals negative log 10 minus 9. Log properties. Log 10 is the exponent you raise 10 to get 10. So log 10 simplifies to 1. So we get 1 minus 1 is going to be 0. We get negative log of 1. So the log of 1 has to be the exponent you raise 10 to get 1. And the exponent you raise 10 to get a 1 is 0. Here I have 1 minus 1 is 0. And we get 0 equals 0, which checks. We get an identity saying that this number works. If we try to plug in the negative 1, right here it's going to fall apart because we're going to get negative 1 minus 9. On the right hand side, if we try plugging in the negative 1, we're going to get negative log of negative 1 minus 9 is negative 10. And if you try to evaluate this in your calculator, let's go ahead and try that. Let's keep those changes. If we go over to the calculator and we grab the log function and we dump a negative 10 into it, we are going to get an error, a non-real answer. So we tried to put a number into the log function that was outside the domain of the log function, and it gave us an error message. But with logarithms, really it's just a matter of paying attention to the domain and seeing if you generate an answer that is outside the domain of the log function. So here's another one. So this one is log base. We want to look. We have log base 3, log base 3, log base 3. So our inverse function is going to be 3 to the x, exponentiation base 3. So right here I have a subtraction of two logarithms with the same base. So from video 1, where we looked at the properties of logarithms, we saw that if we had a subtraction between two logarithms of the same base, that we could compact that into a single logarithm where we had the ratio of the inputs. So inside the single logarithm we get x plus 6 divided by x. And now I have a log completely isolated on the right hand side. I have another logarithm completely isolated on the right hand side. I'm going to go ahead now and exponentiate base 3. So 3 to the log base 3 of 5. 3 to the log base 3 of x plus 6 over x. And the exponentiation base 3 will cancel the log base 3, giving us the 5 that's inside the log function. Exponentiation base 3 will cancel the log base 3, giving us the stuff inside the log function. And now it looks like I can multiply both sides by x to get 5x. X plus 6. I'm just trying to get x by itself, so I'm going to subtract x from both sides. And I'm going to divide both sides by 4, which simplifies to 3 halves equals x. And notice that that's going to be in the domain, because for this logarithm I see that x has to be bigger than 0 to be positive real numbers going inside there. And to get positive real numbers inside of there, I need x plus 6 to be greater than 0, which means x has to be greater than negative 6. The more stringent restriction is that x has to be bigger than 0, and 3 halves is bigger than 0, so life is good. So here I have a logarithmic equation that has the natural log, so I know this is base e logarithm. So the inverse is going to be e to the x. I need to isolate the natural log, so I'm going to go ahead and rewrite my equation. To start the isolation process, I'm going to add 6.9 to both sides. So negative 5.1 plus 6.9 is 1.8. And I have 3/4 the natural log of x equaling 1.8. Instead of dividing both sides by 3/4 to isolate the log function, which just creates a mess over here, instead of dividing by 3/4, I'm going to multiply by the reciprocal, 4/3. So times 4/3. 4/3 times 3/4 is 1. 1 times the natural log of x is just the natural log of x, which equals, this will simplify a little bit. 3 will go into 1.8, 0.6 times, and 4 times 0.6 is going to be 2.4. And now I've isolated the natural log, so I'm going to put the natural log in the exponent position on e to the x, or exponentiate base e, e to the 2.4. E to the exponentiation base e cancels the logarithm base e, leaving us with the x that's inside the function. So we get e to the 2.4 is the exact answer. If we needed to approximate this, we would do it with our calculator. So over here I would need to do e to the 2.4. So e to the x, because it's the inverse function of the natural log of x, is paired with the natural log function on the calculator. So I have to go second natural log to get the e to the x, and I would type in the 2.4 and hit enter, and I get about 11. So it would depend on where you had to round to. If it were to the nearest tenth, it would be 11.0, nearest hundredth 11.02, the nearest whole number we would round to 11. So it would just depend on how the assignment had indicated you should round. All right, last example, we have a natural log again. We can't just go e to the stuff. We have to get one natural logarithm on one side, one natural logarithm on the other side. I see students do this, and you will get marked off in horrific ways if you just go like this. You will be in trouble. So you need to show work carefully. You have a natural log of x plus natural log of x minus 2 equals natural log of 4. We have the sum of two logarithms with the same base. So the log properties indicate that we can rewrite this as a single logarithm on the left-hand side, where we have the logarithm of the product of the inputs. Now I have a single logarithm on the right side, a single logarithm on the left-hand side. So I'm going to exponentiate base e. So e to the natural log of 4, e to the single logarithm on the left-hand side. The exponentiation base e cancels the log base e, leaving us with the stuff inside the logarithm. And if we square this out, x squared minus 2x, or if we distribute the x into the parentheses, I have a neighbor kid running around the yard. So if I were going to try to factor this, I would subtract the 4 from both sides. And then I would need a product that gave me a negative 4 and add it up to negative 3. And that doesn't come out nicely. It doesn't work nicely. So I'm going to go ahead and leave it in this form. And I'm going to complete the square on this. You could subtract 4 from both sides and use the quadratic equation would be another way to solve it. So again, you have choices here. I'm going to complete the square just because I'm going to. So I'm going to take the middle coefficient, I'm going to divide it by 2 and square it, which means I'm going to be squaring a negative 1, which is going to give me a positive 1. So I add 1 on both sides to complete the square. That gives me 5 on the right hand side. Whose square did I complete? I completed the square generated by squaring an x minus 1. Minus 1 is the thing that got squared, so here's my minus 1. I take the square root of both sides. I go plus or minus the square root of 5, x minus 1. And then add 1 to both sides, so I get 1 plus or minus the square root of 5. And just like we saw a little bit ago, because we generated a quadratic equation in the solution process, this generated two solutions, which may or may not be solutions to our logarithmic equation. And we need to go up here and check a little bit. We say, what's the domain? Well, I know I need to put positive real numbers into my log function. So for this to be a positive real number, x would need to be greater than 0. And for this to be a positive real number, I would need x minus 2 to be greater than 0, which means x would need to be a number bigger than 2. And then we want to think about the square root of 5. What's the square root of 5 look like? Well, the square root of, if I put 4, 5, and 9, I know that 5 lives in between those guys. So if I take the square root of all three sections, I get square root of 4 is 2 is less than the square root of 5 is less than 3. I know that the square root of 5 is a number between 2 and 3, and it's going to be closer to 2 than to 3 because 5 is closer to 4 than to 9. So it's going to be a little bit, square root of 5 is going to be a little bit bigger than 2. So when I analyze this, I say, hey, it's 1 plus a number that's a little bit bigger than 2 is going to give me a number a little bit bigger than 3. And a number bigger than 3 is going to be bigger than, that's that. Add 2 to both sides here, and you get x has to be bigger than 2. I don't know what was going on in my brain there. Anyways, this is the more restrictive. X bigger than 2 is more restricting than x is greater than 0. So we're restricted to answers that are bigger than 2. 1 plus a number bigger than 2 is going to be a number bigger than 3. So that will satisfy the need to be bigger than 2. But 1 minus a number a little bit bigger than 2 is going to be negative. And a negative number will not be bigger than 2. So we're going to have to throw the negative answer away. So we wind up getting x equals 1 plus the square root of 5 as the solution. 1 minus the square root of 5 is negative. It's less than 0. So it is not in the domain of the natural log of x minus 2 sitting up here. I'll get a negative number if I plug it in, and it won't work. So I throw this solution away, and I keep the solution that's in the domain of the natural log functions.